What we did was considered the 6 revolute manipulator, set up the reference frames on each link, define the linkage parameters and the join variables, and then we saw what the general form of the transformation matrix is from one link to the previous link. This is a 4x4 homogeneous transformation matrix, and using them we can very easily solve the forward kinematics problem, where given the join variables and the linkage parameters and the end effector position and the given the join variables and the linkage parameters, we need to determine the end effector position and orientation represented by this 4x4 matrix, and that is obtained very easily by multiplying these 6 transformation matrices which are fully known to us. Right? So that problem was very easily solved. The more complex problem in this particular case for the serial manipulator is the inverse kinematics problem. Let us now define that and use the same machinery to solve that. So the inverse position problem is as follows. We are given the parameters of the mechanism, in the case of the 6 revolute manipulator we had di's are fixed parameters. We are also given the end effector position and orientation. We need to determine the join variables, which would take the end effector to the given position and orientation. So this is the problem to be solved. Physically, the position and orientation of the end effector is given, the parameters of this mechanism are given. We need to determine the 6 joint angles. They are this rotation, the shoulder rotation, the elbow rotation, and the 3 rotations at the wrist, so as to take the end effector to the position and orientation given to us. So how do you think this can be solved? I would like you to look at the skeletal diagram of the mechanism that we had drawn earlier for setting up the reference frames. Remember, what is given are position and orientation of this reference frame x6, z6, y6. The key concept used for solving this is very similar, is almost the same as what you had used for the 3 revolute planar manipulator which we saw in the first class itself. Right? The thing to recognize is the following: because the wrist is concurrent, this particular point on the wrist turns out to be a fixed point on the end effector. If you look at the end effector x6, y6, z6, and if you look along the z axis, backwards. This particular point is at the distance d6 on the z axis. It is nothing but the point 0 0 minus d6 on the end effector reference frame, right. So then the position of this particular point in the global reference frame can be very easily obtained, because we know the end effector reference frame position and orientation, right. So the global position of this point is very easily obtained, fine. Now the global position of this point can be obtained in terms of the 3 rotations before that particular point, that is theta 1, theta 2 and theta 3, because this point is also a fixed point on the third reference frame, third link's reference frame. So if you look at x3, y3, z3, this particular point, if you look along the z3 axis, this point comes at the distance d4 from the origin. So this point is nothing but 0 0 d4 in the third reference frame, fine. So this is the key concept used for solution. Let me note it down. So if you take the reference frame, I say z6, x6, let this be y6. The point of concurrency, let us call it point C, is at distance d6 in this direction, and the same point is on the z3 axis, a fixed point on the third reference frame. Find the distance from here to C is d4. So we can write the following: the global position of this particular point is xc this being we are going to use 4-dimensional transformation matrices, so we have to augment this vector, make it a 4-dimensional vector. This equal to this particular point expressed in this reference frame pre-multiplied by this transformation matrix. So that is 0 0 minus d6 1 is minus d6, right. This equal to 3 with respect to 0 So the solution of the inverse kinematics problem becomes very simple because of the existence of concurrent wrist. If the wrist is not concurrent, we do not have this symbol forms. So how do we proceed next? By the way, this is in the 0th reference frame, so I indicated by a 0 here. This is now fully known numerically. All the 3 parameters xt, yc and zc are known, because this is fully known and this is fully known, right. So these three values are fully known. What about this? This contains thetas. This contains the three thetas, theta 1, theta 2 and theta 3. So we cannot find it out numerically because we do not know the values of theta 1, theta 2 and theta 3. So when we multiply this, we get a vector 4-dimensional in which the first three elements are known as functions of theta 1, theta 2 and theta 3. Now if you equate those to the numerical values, we will be able to determine the unknowns theta 1, theta 2 and theta 3. So that is how we proceed. This involves some trigonometry. I will go through that. Fine. So we know xc0 numerically. I am writing out the expression, you can derive it later. So this expression 1, you will see that xc0, that is the global position of the concurrency point C, the x coordinate of that, is a function of all the three angles, theta 1, theta 2 and theta 3. Right. Similarly, y, the same expression in the bracket, so I do not repeat it, minus is d2 plus d3. If you remember, d2 and d3 are occurring in the same direction in the 6th revolute manipulator we saw, so they occur in this club form. Okay, this is expression 2 and y is at c0. This, what is there in bracket, is exactly the same as this. Fine. This is the third expression. Now you can derive theta 1, theta 2 and theta 3 by appropriate manipulations here. I will broadly indicate what the steps are and give you the final expressions. Okay. Now if you look at these first two equations 1 and 2, if you multiply this by sin theta 1 and this by cos theta 1 and subtract, sorry, not this one, the second equation, by cos theta 1 and subtract, this entire term disappears. Okay, and then you will get the following simple expression. I will indicate multiplying subtracting, we get the following. This also simplifies because you get sin theta 1 sin square theta 1 cos square theta 1 added to 1. So, you get this simple expression. No, this will be d2 plus d3 sin square theta 1, and this is minus d2 plus d3 cos square theta 1, one minus the other. Okay. Now, using the following we introduce an angle beta here in order to solve that. So, let cos beta equals xc0 divided by root of and similarly sin beta yc0 if you use that substitution, use that and substitute, you get the following. You can get the following expression: theta 1 what is done here is take these two outside, I mean take this particular term outside. So, you get cos beta sin theta 1 minus sin beta cos theta 1, fine, the whole multiplied by this term. Okay. So, you get the following now. This can be done in different ways. It is not necessary that you have to do it this way. So, this is expression for, if I call this 4, this is 5, the expression for theta 1. So, when you get an expression like this, you are going to use this to calculate theta 1. So, under what cases do theta 1 exist? What are the number of solutions? These are things you have to understand, right. So, in this particular case, look at the expression. Under what conditions do you think theta 1 cannot exist? There is no answer for theta 1. Yeah, the argument of sin inverse, if it is greater than 1 in magnitude, then there is no solution for that, right. So, what about tan inverse? Yeah, but there are solutions minus infinity to infinity, there are solutions for tan inverse, right. How many solutions are there? Look at this expression, how many solutions are there? 4 solutions, 2 for sin inverse, other 2 for tan inverse. We know both the projections x and y numerically, right. So, we can find out which quadrant it lies in. So, really there is only one solution for this, there are 2 solutions for this, fine. So, argument of sin inverse not being within the allowed range, what does it indicate physically? This is another thing that one has to understand. Yes, is beyond the reach, but beyond the reach where? So, if you look at what we had used, x0, x0 and y0 are the projections on the xy plane of the global frame, right. So, we are looking at the manipulator in that projection. Okay. So, let us see the manipulator in that projection. And I am going to draw it stretched out along the x0 direction the way we did. If you do that, then what you get is, I'll bring back the figure again to you. This is what we see, fine. So, there is a first post, this is a z0 axis, and then this link is offset like this link is offset like this. Finally, this is the point C is somewhere along this, okay. So, if I draw it here, C is somewhere along this. Now, if you move theta 2 and theta 3, which is essentially rotating this about the shoulder and rotating this about the elbow, what happens to the point C is it is taken to some point on this plane, okay. And what does theta 1 do? Theta 1 rotates the entire thing. Now, so theta 1's ability, what theta 1 does is position this particular plane, okay. Suppose the point is somewhere here, the point C is actually here, the given position is here. What theta 1 does is bring this plane into coincidence with this particular point, its projection in the xy plane, right, rotate it to bring this particular line actually, which could stretch from minus infinity to infinity, because in this particular calculation you do not know the restriction whether it is reachable or not with regard to theta 2 theta 3 motion. Only with regard to theta 1 are we really calculating it, fine. So, this entire plane is brought into alignment with this, okay. How many ways can one do that? How many solutions for theta 1 is there for that? There are two ways you can do it. You can bring this side here or you can bring this side, okay. So, those are the two solutions. When is it that it does not have a solution? It does not have a solution when C falls within this circle. If this particular point comes back to x0, then this plane will pass through the origin, and in all cases theta 1 will have a solution, because you are moving a plane or this particular line in this projection which is passing through the origin, and you are rotating it about the origin. So, that line can reach all points on the plane, right, whereas if the line is offset like this, then you cannot reach inside this particular circle. So, the situation of there being no solution for theta 1 corresponds to this, that C is somewhere here, fine. And the situation where there are two solutions is when this plane gets aligned with the point C, or made to pass through the point C, and you can immediately see that can be done in two ways, okay. So, d2 plus d3 is too large, that is, so that, and that is larger compared to this, larger than this in magnitude, right, that is this C turns out to be inside that circle, fine. Okay, there one more thing, I had used this tan inverse. So, when you finally calculate it using a program, use this function a tan 2. So, A tan 2 takes two arguments, the y projection first and the x projection next, and it gives a solution in from between 0 to 2 pi in the full range. Okay, so it will give it in the exact quadrant. There is only one solution for that. Okay, so that is theta 1. So similarly, we can proceed to calculate theta 2 and theta 3. We proceed in steps. So now that we have theta 1, using numerical value of theta 1, remember one of the two solutions that you got, and then you proceed with the calculation. While you do it, you do not use the other solution randomly, fine, you have to be consistent. Either from 1 or 2, which is the first two equations for x0, xc0 and yc0, we get the following expression: d4 sine theta 2 plus theta 3 plus a2 cos theta 2 I will write both the expressions. There is a reason for that. Fine, I just substituted theta 1 in the first equation to get this, or equivalently I could have substituted in the second equation to get this. I am getting numerical value for this particular expression. Now, what is the relevance of saying you could use one or the other? You could have used just one. Well, you cannot use this when cos theta 1 is 0, right? In that situation you need to use this. When cos theta 1 is 0, sin theta 1 is either 1 or minus 1. So you need to use this, fine. So calculation has to be numerically, or it has to be defined, determinable. So you can use one of them. Okay. So let's call this equals b1, let's say. So b1 is known numerically, fine, and we write equation 3 as just rewriting it minus d4 cos so let us call this b1 because this is fully known. This is b2, this is fully known, so we are just giving two names for that. This is a2, by the way, sin theta 2, fine. Now we can eliminate either theta 2 plus theta 3 or theta 2, one of them. What we do is, let us eliminate theta 2 plus theta 3. That can be done by transposing a2 plus cos theta 2 to this side, a2 cos theta 2 to this side, a2 sin theta 2 to this side, squaring and adding. You eliminate this theta 2 plus theta 3. So I will simply say eliminating The way it is done is the way I described. We get d4 square as sorry yeah, to this, okay, cos theta 2 fine. Then isolating this particular term b1 cos theta 2 and b2 sin theta 2. We know b1 and b2 numerically, fine. We do that. Let this expression be 6 and let this be 7, okay. So we get beta 1 b1 cos theta 2 plus b2 sin theta 2 So assuming A2 is non-zero, otherwise assuming A2 is non-zero, we get the following. From this we get the following, essentially the same way. You take root of b1 squared plus b2 square outside and call b1 as root of b1 square plus b2 square cos some angle. Similarly, this is sine the same angle. Using that, we finally get theta 2 as follows. This is the expression for theta 2. You get it essentially by these eliminations. So that is the other angle. Again, let us inquire about solvability in this particular case, number of solutions. This second angle A tan 2 is fully obtained, beta B2 and B1 are known numerically, so we know that uniquely, you can get it uniquely. What about this? The same problem with argument being outside the allowed range could be there. So this could be more than 1 in magnitude, in which case there is no solution here. If it is less than 1 in magnitude, there are 2 solutions. If it is equal to 1 in magnitude, there is 1 solution. These are the various ways in which solution occurs, right? And what does it mean physically? The 2 solutions and no solutions. Again, it's an issue of reachability. Okay, only now we look at reachability in another plane. So earlier, if you remember, we looked at reachability in the x y plane of the global frame, right. Now we are looking at reachability looking at a plane in this direction along the join 2 and join 3 direction. If you look along that, you get a projection of the manipulator. It is in that plane that we look at reachability for this particular calculation. So if you do that, then what transpires is the following. This comes from cosine rule, which is used when we know 3 sides of a triangle. So the sides that we are talking about is essentially this. We see the manipulator like this, let us say the elbow up position. This is the point C. This is some reference frame in which we are now having these projections. This is B1 and this is B2. This particular angle is the tan inverse that you are seeing here, and this particular angle is the cos inverse that you are seeing. Fine. The solution that we have here, we said there are 2 solutions for this. So if you get an angle here, the negative of that also is a solution. Fine. So the solution is essentially this angle plus or minus this. Okay. So this is the way I have shown, this is the minus solution. The plus solution is the symmetrically reflected solution. Fine. And what are the sides? The 2 sides are, this is A2 and this is D4, and this side is root of B1 squared plus B2 squared. So this expression corresponds to this picture. So again there are 2 solutions possibly for theta 2, and when is it that there are no solutions? Well, algebraically, when this particular argument goes above 1 in magnitude, but geometrically, clearly in this picture there is a limit to reachability of these 2 lines, right. They have to be joined always here, and the length is fixed. So if you consider that, if let us call these points A and B. So if this is A and this is B, and if D4 is this length, the set of points C can reach are obtained like this. Rotate this link BC with B as center, you get this circle. This was done earlier when discussing configurations and workspaces. Right. Now rotate this circle about A by rotating AB. Rotate AB, take the circle along with that, and you get this annular region then as a set of points C can reach. If the C that is given is inside this or outside this annular region, it cannot be reached. That will be indicated by this. Okay. There is a particular situation when that inner reachability is complete. There is no void here. When is that? When does that occur? Yes, when A2 and D4 are equal, then there is no problem with the inner reachability, because this will fold up to this point, right. And if you look at nature's design, our hand is more or less like that, right. We can scratch the shoulder, So that is actually the configuration which is the maximum volume index, a normalized volume index. Okay, so this is the physical interpretation of this solution. So up to now, how many solutions are there for theta 1 and theta 2? Now there are 4 solutions. There are 2 solutions for theta 1, and for each value of theta 1 there are 2 solutions for theta 2. Altogether there are 4 solutions. And now for the final angle theta 3. I hope I have written down equation 6, 7, yeah. And once you obtain this, it turns out that theta 3 based on that will be so d4 should be non-zero. For there to be a solution, b4 has to be non-zero. And you can obtain the solution for theta 3 like this. This is equation 9. How many solutions are there for theta 3? Yeah, from this expression just one solution. But if you go with the possibilities for theta 1 and theta 2, only theta 2 is occurring here, right? So how many solutions are there for theta 2? There are 4. So theta 3 will have corresponding 4 solutions. You need to, for each theta 2, you will have theta 3 obtained from this expression. Okay. So this is the solution for the first 3 joints of the manipulator. This is one of the most common manipulators, and in terms of complexity, this is more complex than Skara, cylindrical or spherical, because you can have more complex manipulators than all this. But okay, so this is the solution for the first 3 angles. What about the last 3? Theta 4, theta 5, theta 6. Remember that we know the orientation of the end effector. Now we know the orientation of the third link. The theta 1, theta 2 and theta 3 are known, right? So in this, I split this as R3 with respect to 0 and R6 with respect to 3. because in this matrix only theta 4, theta 5 and theta 6 occur, and in this matrix theta 1, theta 2 and theta 3 occur, and we know this entirely numerically and this also entirely numerically, because we have just now found theta 1, theta 2 and theta 3. So we can calculate this, fine. So then theta R6 with respect to 3 can be obtained numerically, okay, as R3 with respect to 0, inverse of that, which is the same as the transpose of that, into R6 with respect to 0. You will see that this transpose is nothing but R0 with respect to 3. That is how this becomes R6 with respect to 3. Okay. So what we have here is that we have the right hand side numerically, we have this matrix numerically. We also have the expressions for the 3 matrices which get multiplied in order to give us this. So we can express the elements of this in terms of theta 4, theta 5 and theta 6, right. So each element of this matrix can be expressed as a function of theta 4, theta 5 and theta 6, and we know each of those elements numerically, okay. So that particular expression for the matrix, you can multiply out those linkage transformation matrices and you will find the following. First row, each element is known numerically and we have the expression for each element in terms of theta 4, theta 5 and theta 6, fine. Let me call the elements as R11, R12 and so on up to R33, okay. Now this is more or less the matrix you will get to the following question. If the orientation matrix is given, how do you find the Euler angles? For the 3, 1, 3 Euler angles, the matrix will turn out to be more or less the same, fine. So that, if you remember, that is one of the problems I had asked as an exercise. The solution to that also turns out to be the same, okay. Now look at the solution. Theta 5 can be obtained first. What is it? Cos inverse of minus R33, right? How many solutions? There are 2 solutions. Now what about theta 4 and theta 6? if you look at this element, these two elements, you will find that you can get theta 6 immediately, because theta 5 has been determined now, right. So you can get cos theta 6 and sin theta 6 from these elements. And then what about theta 4? That you can get from here, right. But we have to be sure of one thing. In these we have to divide these elements by sin theta 5, because we have found theta 5, and sin theta 5 cannot be 0, otherwise we cannot do this calculation, right. So if sin theta 5 is non-zero, then we can very easily calculate theta 4 as using this. This is R 23 divided by sin theta 5 and R 13 divided by sin theta 5. Similarly, theta 6 equals a tan 2 from here minus R32 divided by sin theta 5 comma R31 divided by sin theta 5. This is fine. So what if this is equal to 0? There are two possibilities. When sin theta 5 is equal to 0, this could be 1 or minus 1. Cos theta 5 could be plus 1 or minus 1. Essentially theta is 0. In the other case theta is pi. Theta 5 is pi. So in this case you can obtain using these elements. Cos theta 5 is now 1, substitute that here, fine. Using that you can obtain theta 4 minus theta 6 fine. So we have taken care of all the possibilities. So I will just to make it explicit say this is equal to 0 and cos theta 5 equals minus 1. That case theta we get theta 4 plus theta 6 . So this is the procedure for calculating theta 5, theta 4, theta 5 and theta 6. It has taken care of all possibilities. How many solutions? Just two solutions. There is a possibility, that is if theta 5 is less than that is R33 is less than 1 in magnitude, there are two solutions. If it is equal to 1 in magnitude, no. We are calculating if that is equal to 1 in magnitude, if it is 1, then there are an infinity of solutions. We can get only theta 4 minus theta 6. Or if it is minus 1, again one solution for theta 5. Theta 4 and theta 6 have infinity of solutions, provided this adds up to this. In case of cos theta 5 is minus 1 and the difference between the two is equal to this in the other case. So when theta phi has one solution, there are an infinity of solutions for the total 3 angles. When theta phi has 2 solutions, there are only 2 solutions for the whole set. So third thing is there a case where there are no solutions? Well, that will not happen if that matrix R11 to R33 that we had obtained numerically is a proper orthonormal matrix. It will not happen. Right? So that we have to ensure, and all these matrices are orthonormal with determinant 1. So that is ensured. Okay. So this is the full solution for Puma or manipulators of the same configuration. Okay. So it is fairly simple in the sense, once you write it down correctly, you can calculate it very easily. Okay. Here and there I kept saying that D4 shouldn't be 0, A2 shouldn't be 0. What happens if those are 0? These are things you can figure out physically. Try to do that yourself. Okay. Such manipulators are not used, but those are trivial cases. We'll proceed with some more discussion of inverse kinematics in the next class.